A very good morning and welcome back to this session. In the last session, we have seen about the theory and application of UV visible spectroscopy. In this session, we will talk about infrared electromagnetic radiation and how it interacts with organic molecules. Okay, so let's have a look at the infrared spectroscopy. Now, the first thing is that many organic molecules, they absorb in the UV visible region, and this absorption takes place at the electronic level, or it excites an electron from a lower molecular orbital, higher molecular orbital. But IR radiation, on the other hand, is slightly of lower energy. So that is one thing to note, and because of that, it will not be able to excite the electrons. Instead, the excitation takes place on the vibrational levels, and because of this, the interaction of IR radiation with molecule is mostly on the vibration of a bond. Okay, so let's see some of the characteristics. IR radiation is the most widely used tool for the detection of functional group in pure compounds and also in mixtures. That is one of the important things. The process is rather quick, and you can obtain the spectrum in just minutes, and you can also use just a small amount, just a few milligrams of the compound, and the compound also can then be recovered. So there's no loss of the compound after the spectra is taken. And the third point is that, just like I have mentioned earlier, the infrared electromagnetic radiation, they have lower energy because they are obviously have longer wavelength than the UV visible electromagnetic radiation. Now these vibrations, they are quantized, and as they occur, the compounds absorb infrared energy in just particular regions of the spectrum. I mean, it's not like a broad spectrum, they absorb at specific regions. So that is one of the important qualities of infrared spectroscopy. The position of IR absorption band is specified in frequency units, just like we have seen for UV visible. It is expressed in terms of wavelength, but if you remember the first theory that I have shown you, wavelength and the frequency, they are related to each other. But here we are not going to use the frequency, that is nu value, h nu, that we have seen earlier. What we will be using is this wave number. Okay, so this is another form of measurement of frequency. Now the wave number is measured in reciprocal centimeters. Okay, so that is one of the important thing. Or you can also express the position of the IR absorption in wavelength, that is measured in micrometers, not in nanometers, it is measured in micrometers. Now you can see here the relationship. The wave number is equal to 1 by lambda. Now the difference here is that the nu value is nu equals to c by lambda. If you remember, this will be c, but then the relationship is still similar. Okay, it is still, the frequency is indirectly or inversely proportional to the wavelength. Now the unit of the wave number is in centimeter inverse, or you can call it as reciprocal centimeters. Now IR spectra is a plot of percentage transmittance versus increasing wavelength or decreasing frequency. Now most of the spectra, IR spectra, they are represented in terms of decreasing frequency, that is wave number, rather than the wavelength. So we will be looking at most spectra expressed in this form. Now here the difference is that these are expressed in percentage transmittance and not absorbance. It's just the opposite to that of the UV visible spectra. So that was the main difference there. So what do you see here is that a dip in the spectrum is called a band or a peak. In the UV visible, a rise in the spectrum is a band or a peak, but here it's a dip, that is the band or the peak. So these are the differences. We'll have a look at the schematic diagram of an absorption spectrometer, and in this case is for IR spectroscopy. So as you can see here, we have a beam of infrared light from here, the IR source, and this beam split into two regions similar to that of UV visible also. One will pass through the reference and one will pass through the sample. Then this will then go to the detector, and then it is processed, and finally the graph is plot. So that was the thing. It's quite similar in principle to that of the UV visible. Now this is just a very simple diagram representation of this. Now the reason why you use the same beam to pass through a reference and the sample is to avoid any error. Say in the olden days, what they used to do is that they would first irradiate a reference sample and then record that. Then later on they'll do irradiation on the sample, but then difference in time, there might be difference interaction, and because of that there might be some error. So by doing this, at the moment when you are recording for the sample, you are also recording for the reference, and that will minimize the error of the instrument. Now there are two ways in which the IR spectroscopy can be taken. One is the sweep way. That means you start with a frequency of about 4000 wave number, then you slowly change the frequency till you reach 600 wave numbers. Okay, so in between these, and then you plot a graph, but that will be like it will take time for the work to complete, because you have to take each frequency and then refer and then check and then plot the graph. But modern instruments, they are able to broadcast the whole frequency, and they use a technique known as Fourier transform, and the most commonly used term is FTIR, Fourier transformed infrared instrument. Now what this instrument do, I'll not go into the detail of this instrument, but in a simple understanding is that all the wavelength are broadcast at the same moment, and then you'll get the different frequency, different interaction. You have to transform that into, so you'll get like kind of a raw data. From the raw data you transform into the different frequency. So from the whole frequency you transform it into different sets of frequency, and then you can plot the graph. This will be faster. It will take just in minutes. It's not like when you do a scanning type of spectroscopy. So I'll not go into the detail of the technique of Fourier transform. If you are interested, you can read about Fourier transform. There are many available sources on that. But the main difference is that scanning and Fourier transform will speed up the process rather than the scanning method. So this is a typical IR spectra. Here we have the transmittance from 0 to 100. Here we have the frequency in wave numbers, and as you look here, transmittance means no light has been absorbed. If there is no absorption, then transmittance will be around 100. If there is absorption, the transmittance can go down to 0. So here we see a dip in the spectra. So this is called as a dip. Here also we have a dip, but this intensity is less. Okay, so we read the IR spectra upside down. If you look at the UV visible, the spectra looks something like this, and then you have a band like that. So we have a hillock in the case of UV visible. But everything will be the same, it doesn't matter. It's just that IR is plotted in such a way that you plot the transmittance percentage versus the frequency. Now the question is, which molecules will be IR active and which molecules will not be IR active? In order for a vibrational mode in a sample to be IR active, it must be associated with change in dipole moment. What does this statement exactly mean? It simply means that organic molecule in which the vibration cause a change in the dipole moment. So, if there is a change in the dipole moment due to vibrational mode, then that molecule will be IR active. Okay, so let us try to understand this part. If you look at covalent bonds, you might think that this bond is rigid. So, carbon and hydrogen bond is fixed, but actually it behaves more like a spring. Okay. So, covalent bonds, they behave more like springs. I can represent this in this form. So, we have a carbon, we have a hydrogen, and if you see springs, they can be stretched or they can be contracted. If you have a spring, you can do that. Let me just show you. I have something here, not exactly a spring, but if you look at this cord, okay, at equilibrium, suppose it's this much. Now you can stretch it further, or you can come back to that same location, or you can compress it more, but there will be a point where you cannot compress further. Okay. So, a covalent bond also behave like a spring in this form. So, it can either be stretched, compress, stretch, compress, and there will be an equivalent length or equivalent point where this is known as the bond length. Okay. So, let us try to understand this better, how it interact with IR. So, the carbon hydrogen can either stretch, it can stretch in this way, okay, or it can then contract also. So, let us say this is the equivalent position, this is the stretch position, and this is the contract position. If we plot a kind of a graph starting from this point, then it will look something like this. As it stretches, it goes to this side, and then it come back to the equilibrium point, it contract, come back to the equilibrium point. It's not it. So, this represents an interesting thing. It looks like a wave, and because it looks like a wave, it would have frequency of stretching. So, when the molecule stretch or contract, it will behave as a wave. That is one important thing to understand. So, now if you have a waveform, you have a wavelength, and the wavelength is defined by nu equals c by lambda. So, that means you have a particular wavelength, you have a frequency. Now, we have wave number can be expressed in this form. So, again it is the same thing, you have the frequency in wave number and the wavelength. So, these two will be related to one another. What do we see here? If suppose the same frequency match that of the IR frequency, when it match the IR frequency, what we observe is that there will be an absorption, okay, because they have the same frequency. The IR frequency and the stretching frequency, they are the same. So, if suppose the frequency is blue here and the IR frequency also is of the same length, instead of cancelling the frequency or cancelling the absorption take place, and when absorption take place, the intensity is slightly more. You can see this wave, you still have the same wavelength, just it is of higher intensity. That means the molecule now absorb the radiation, and when it absorbs the radiation, then it is intensified. This is a simple way to understand how a molecule interact with IR radiation. So, it is because covalent bond, they can either stretch, they can either contract and vibrate. So, between two atoms. So, we will come back to that statement earlier. In order for a vibration mode in a sample to be IR active, it must be associated with change in the dipole moment. So, we need to understand first what is a dipole moment. I think you can still recollect or can still remember what is the meaning of a dipole moment. It is mathematically given by mu equal to delta d. Now, delta here it does not mean the change. Delta here is the charge. Okay. So mu is the bond dipole moment, d is the distance between the partial charge. So if a particular bond, the electronegativity between the two atoms is different, then the bond will be polarized. So if a polar bond is there, then then the bond will be separated by two different partial charge. So the distance between the partial charge and also delta here means this value of the partial charges. So that is a dipole moment in a bond, but this is a bond dipole moment. It is a vector quantity. That is one of the important things that we need to remember. And for a molecule, the total molecular dipole moment is exactly like an approximated as the vector sum of the individual bond dipole moments. So the dipole moment of a molecule will be the sum of all these small bond dipole moment. Now let's take a look at these examples. For a bond to be polar, the electronegativity of the two atoms should be different, like bromine and hydrogen, hydrogen and chlorine. Okay. If they are of the same simple diatomic molecule, the bond will not be polar. And if the bond will not be polar, that means this partial charge will be 0 and mu value will be 0, so there will be no dipole moment. But if a bond is polar, then we have this partial positive charge, partial negative charge, partial positive charge, partial negative charge. So this will have a dipole moment. Now it is a vector quantity, and because it is a vector quantity, now by convention it was always represented in the form of an arrow starting with a plus like this, and this plus here is for the positive end and the arrow goes into the negative end. So that means the dipole moment of these two molecules can be represented as such. Let's take a look at another example. Carbon dioxide molecule. Carbon dioxide molecule has got two polar bonds, carbon oxygen bond, carbon oxygen bond. Carbon is partially positive, oxygen is partially negative. Because the dipole moment is a vector quantity, so we saw these two dipoles with equal in magnitude in opposite direction, so they cancel one another. So as a molecule, this does not have a dipole moment. As individual bonds, there will be dipole moment. This carbon oxygen bond has got a dipole moment, this carbon oxygen bond has got a dipole moment, but as a CO2 molecule, it does not have a dipole moment. So from here we can easily understand that there are molecules which contain bond dipole moment, but as a molecule they will not have a dipole moment. So even though carbon dioxide is not having any dipole moment, if we look at the different stretching mode of carbon dioxide, we can understand why it can still be IR active. Because if we look at this statement which says that it must be associated with change in the dipole moment. So even if carbon dioxide doesn't have a dipole moment, but it will still be IR active, because if there is stretching, there will be some stretching modes that can be IR active. So let's have a look at this particular case. So now you can easily say, you can make a statement that all molecules that has got a dipole moment, they should be IR active. Like even water molecule, it has got a permanent dipole moment, therefore it will be IR active. But all simple diatomic molecules like hydrogen, bromine, chlorine, nitrogen, oxygen, all these molecules, they will not be IR active. Now some molecules, they may not have a dipole moment as a molecule, but they can be IR active if any of the stretching will lead to changes in the dipole moment. So let's have a look at the case of carbon dioxide. Now carbon dioxide, it can have this kind of stretching. This side and this side stretch equally at the same time, or it can contract equally at the same time. Now here, if you look again at that formula of a dipole moment, mu equals delta d. Distance is the same on both sides. Distance is the same on both sides. So what does this mean? It means that there will be no change in the dipole moment. If it stretch, here dipole moment is 0, here dipole moment also is 0. So stretch or contract, both dipole moment are 0. This is known as symmetric stretching. Okay. So all symmetric stretching will not have a change in the dipole moment in case of carbon dioxide. Now let's take a look at the second possible stretching. Now this molecule can stretch only on one side or only on this side. So what will happen now? Now because this distance is longer than this side, therefore the magnitude of the bond dipole moment will be different between these two. So that means there is a change in the dipole moment of the molecule. If both the length are same, dipole moment will not change. But here one is shorter, one is longer. So again by that calculation, mu equal delta d. Here the d value is greater than the d value of this side. Therefore this dipole moment will be higher in magnitude than this one. And at the end result of that is there is a change in the dipole moment. So either it stretch on this side or it stretch on this side, there will be a change in the dipole moment. So this is known as asymmetric stretching, and because of that this will be IR active. Then we have the third mode of, this is known as bending. So instead of stretching outside, this molecule might bend like this. Okay. So when it bends, it will become like this one. The structure changes to this. Now here we can see that there's a change from a molecule without a dipole moment, with zero dipole moment, to a molecule with some dipole moment, because now we have the direction is in this way, and we have an overall resultant in this direction. So that means now we have a dipole moment from zero dipole moment to some value of mu. So again this means we have a change in dipole moment. So this mode also is IR active, this mode is IR active, and this is not IR active. Then we have the third one. Again this is a combination of asymmetric stretching along with the bending mode. So this will also be IR active. So we can see here that earlier statement which says that there should be a change in dipole moment for a molecule to be IR active. So it is not required to have a permanent dipole, but as long as the molecule stretching or bending produce a kind of change in dipole moment, the molecule will be IR active. A molecule can vibrate in many ways, and each way is called a vibrational mode. In general, all linear molecules can have 3n-5 degrees of vibrational modes. So this is only for those molecules with 3 or more number of atoms. So they have 3n-5 degrees of vibrational modes, whereas non-linear molecules like water, they have 3n-6 degrees of vibrational modes. Now here I have an example of the possible vibrational modes. Now you can see this first one. This is all symmetric, this is also symmetric, and this is also symmetric stretching. This is also sometimes called as scissoring. This is known as wagging. Okay, so it wag. And then these are the anti-symmetric. That means they are not symmetrical. You can see here one is stretching, one is not stretching, and then here also we have this is known as rocking. Okay, and here this is known as a twisting mode. So this can be the possible type of stretching. Now most of the time for linear molecule, the symmetric stretching, they will be not active most of the time, except see this scissoring. Scissoring will lead to a kind of IR active mode, but this symmetric stretching, the first one, this will usually lead to a non IR active mode of stretching. Okay, so any molecule can have these possible type of stretching in their bonds. So because of this possible type of stretching, which will lead to what is called as change in the dipole moment. So if it lead to the change in dipole moment, the molecule will be IR active. Now I'll not go into the detail of the Hooke's law, but this Hooke's law is usually applied on objects that are attached to a spring. Now because we consider the covalent bond to be a spring in nature, and then you have atoms at the two different ends, so you can also think of it in that way. So now here let's first have a look at the spectra. So this is a particular spectra. So we have here the wave number from 4000 to 600, transmittance percentage from 0 to 100. Okay, and this IR spectra is usually divided into different regions. This is a rough division. It's not like an accurate division. It's not always fixed as this, but somewhere around 2500 there is a kind of a division. Somewhere around 1900 there's a kind of division. Somewhere around 1500 there's a kind of a division. So what do we have here? So let's first have a look at this region here. Now in this region, the spectra is mostly of carbon-carbon single bond, carbon-oxygen single bond, carbon-nitrogen single bond. So all the single bond stretching take place in this particular region. If we move on, in this region we have carbon-carbon double bonds, carbon-oxygen double bonds, carbon-nitrogen double bonds. So all the double bond stretching will be somewhere in this region. Of course, just like I told you that this is not a rigid region. Sometimes it might overlap to this side, sometimes it might overlap to that side. So it's not always fixed, but to some extent they are mostly in this region. Then the third one is triple bonds are here. Okay, so carbon-carbon triple bonds, carbon-nitrogen triple bonds. So if you know the region, if suppose you get the spectra of a molecule and somewhere in region of say 1700 wave number, you will know that it will be due to some double bonds, and you can exactly know what kind of a double bond is it, carbon-carbon or carbon-oxygen or carbon-nitrogen. Okay, now this last region, this is due to NH, OH and CH stretching frequency. So you can see these are divided into 4 different regions. But then all these regions, okay, why is it that we have the carbon-carbon single bond or all the single bond in this region, and then we have this single bond on this extreme region? Here we have 600 wave number, that means these are low frequency radiation, and these are very high frequency radiation. To understand that, we have to just look at the simple form of the Hooke's law and not go into the detail of the Hooke's law. Let's have a look at the Hooke's law. Now Hooke's laws talk about vibration frequency of springs. That is, the vibrational frequency is directly proportional to the strength of the spring. So the stronger the spring, the frequency will be higher. Vibrational frequency is inversely proportional to the masses at the end of the spring. So it depends also on the mass. Now, directly proportional to the strength of the spring, inversely proportional to the mass of the spring. Okay. So what does this mean? This is actually not the real Hooke's law mathematical expression. I'm just putting this so that you can understand. So if suppose this is the frequency in wave number, this will be proportional to F by m, where F is the strength and m is the mass. Now we can see here that F here is the strength of a bond. We can relate to that. F as the strength of a bond, and here the mass as the mass of the atoms. Okay, this is a simplified version of the Hooke's law, just for our understanding. Okay, so now keeping this, let's have a look again at that picture earlier. So we have this one. We all know that single bonds are slightly weaker compared to the double bonds. Carbon-carbon single bond slightly weaker than carbon-carbon bonds, double bonds. You need more energy to break a double bond than to break a single bond. Okay. Again, triple bond are slightly stronger than the double bonds. So here we can see, based from this relationship, because the bonds are stronger, therefore they absorb at higher frequency, this region and this region. So triple bonds will absorb at this frequency because they are stronger than the double bonds, and double bonds are stronger than the single bonds. Now, but then these are also single bonds. Now we can see here the effect of the mass. So here the hydrogen atoms, they are the smallest atom in the periodic table, the lightest, smallest, lightest, so their mass are very, very small. So what happened is that because the mass, so we can now consider that the overall mass between this carbon and hydrogen, they are very, very small, and because of that, this is small, that means now the frequency will be high. If the mass is high, frequency will be low. If the mass is low, the frequency will be high. So because of that reason, these absorb at the higher frequency. Okay. So that is the important thing to remember here. If you are interested about the Hooke's law, you can read about this, about the Hooke's law. But of course, this is not the correct expression. This is just a simplified expression that I want to show you, the relationship between the strength of the bonds and the mass of the atoms. Now, these three regions, they give us important information about a molecule. We can know different functional group of the molecules, like say NH2 or alcohol group that is present, CN group, CO group, and then CN double bond. So these are imines, and this is a cyano group. So we can know about the functional group of the molecules. On the other hand, this region is a little bit complicated. Sometimes it does not give us useful information, and this region is somewhere from 1400 to 600. This region is then known as the fingerprint region. It is known as a fingerprint region because it has got some unique pattern. A molecule will have a unique pattern that will be different from other molecule in this particular region. So that means it's just like your fingerprint, our fingerprint, which are different from each other. Here also this region will be different for each molecule. See, suppose here you may have the same, say, carbonyl group. All molecule having carbonyl group has the possibility to have the same peak around this region. But this region, they will have a unique pattern which will be different from others. So that is a very useful part to especially compare between two molecules. If suppose you have a molecule that is unknown to you, you take an IR spectra and you compare with the old spectra that were known. If the fingerprint region match, that means you are sure that they are the same molecule. If suppose the fingerprint region does not match, then you will know that there are different molecules. So this is usefulness of IR spectroscopy. So we have the region which give us the functional group and the region which is the fingerprint region. So that is all for today. I hope you are clear with the concept. We have seen about how molecules which can change, which can have a change in dipole moment, they are IR active. Molecules which does not have a change in dipole moment, they will not be IR active. And then we have seen a little bit about the Hooke's law, more like a trying to understand Hooke's law on springs, where we can also relate to IR spectroscopy, where you have, depending upon the strength of a bond, where will be the frequency that will be absorbed. Stronger bonds absorb at higher frequency and weaker bonds absorb at lower frequency. And also it depends on the mass of the atoms. The lower the mass, it absorbs at higher frequency. The higher the mass, it absorbs at lower frequency. So that's all. Thank you.